Judy was boring.
Hello.
Then Judy discovered ChumbaCasino.com.
It's my little escape.
Now Judy's the life of the party.
Oh, baby, mama's bringing home the bacon.
Whoa, take it easy, Judy. The Chumba life is for everybody. So go to ChumbaCasino.com and play over 100 casino-style games. Join today and play for free for your chance to redeem some serious prizes. ChumbaCasino.com. No purchase necessary. Void where prohibited by law. 18 plus terms and conditions apply. See website for details.
Hello, it is Ryan, and we could all use an extra bright spot in our day, couldn't we? Just to make up for things like sitting in traffic, doing the dishes, counting your steps, all the mundane stuff. That is why I'm such a big fan of Chumba Casino. Chumba Casino has all your favorite social casino-style games that you can play for free anytime, anywhere with daily bonuses. That should brighten your day a little. Actually, a lot. So sign up now at ChumbaCasino.com. That's ChumbaCasino.com.
No purchase necessary. VGW Group. Void where prohibited by law. See terms and conditions. 18 plus.
This episode is distributed under a Creative Commons Attribution Share-alike 4.0 international license. For more information, visit creativecommons.org.
This is Gabriel Hesch from the Breaking Math Podcast. I am thrilled to announce that we have teamed up with a particle physicist and a science fiction author named Dr. Alex Alanis to create a brand new science show on YouTube. Our new show is called the Turing Rabbit Holes Podcast. It's named after the mathematician and father of modern computer science, Alan Turing. You can find us at youtube.com/Turing Rabbit Holes Podcast, and that's spelled Turing Rabbit Holes Podcast. Be sure to like and subscribe for great visual storytelling about the history of mathematics, physics, and computer science and the impact that they have had on society. Again, that's youtube.com/Turing Rabbit Holes Podcast. And now, back to the Breaking Math Podcast. Somebody stole our website.
Oh no, whatever shall we do?
I mean, I guess you could go to the new website, http://breakingmathpodcast.app with no www for all you old timers.
So breakingmathpodcast.app? I mean, if you're into that sort of thing.
Hey Breaking Math fans. First, I want to thank you for listening. I have an important message for everyone. You can start your own podcast right now with Anchor. Anchor lets you create and distribute your own podcast. Just get an idea, record, and upload. It's just that easy. Anyone can do it. I'm on my way to accomplishing my dream, and you can too. Just get on your device's app store and download Anchor. It contains everything you need to make a podcast. With Anchor, you can put your podcast on all the big platforms. Apple Podcast, Spotify, Google Podcast, Amazon, and more. Reach the whole world with Anchor. Best of all, Anchor is free. You have nothing to lose with a free platform. Download the Anchor app or go to anchor.fm to get started.
This is Sofía, and you're listening to a Breaking Math Problem episode. You may have noticed that we have the P1 label. This episode is called P1 Peano Addition, and it's an experimental format. Most of our stuff, we work on a whole topic. For example, for forbidden formulas, we talk about elitism in math. But today we're going to talk specifically about Peano's axioms, and more specifically, how to prove that n plus m equals m plus n. Before we get into all that, we have our guest on, and it is my mom again, Diane Baca.
Hello.
You read the Wikipedia page, and you said it was kind of dense.
Yeah, because it looked like it was calculus-based or set-based or something, and it just was a little intimidating for somebody like me who doesn't have a whole lot of math in their background.
Oh yeah, and set theory is something that's really simple. It's just a collection of things, or like, in a way, it's a collection of things. It generalizes the idea of a collection of things. Mm-hmm. But
can I just say what I think is funny?
Sure.
It's mathy. It's so mathy to say n plus m equals m plus n because it feels like everybody knows that n plus m equals m plus n. Okay, which I think is always funny that math people need to prove things like, n plus m equals m plus n because it seems so obvious.
Yeah, I mean, all of math is kind of like that. And science was an attempt to say that the world is maybe not so obvious. I mean, ideas are tested by experiment. And math is kind of like ideas are tested by ideas. But first, let's do some plugs. You could go to Patreon and patreon.com/breakingmath, and you can order, and you could join our poster tier on there, and we'll give you a poster. If you don't want to support us monthly and you just want a poster, you could go to facebook.com/breakingmathpodcast, and on our store, you could buy our poster for $22.46, and that's pi to the $e plus shipping and handling. I think it's $12.50 right now, but we're working on getting that down. And our Twitter is @BreakingMathPod, and our website is breakingmathpodcast.com. So yeah, the piano axioms, all of math isn't exactly like that. This is specifically formalism that we're talking about today. And it was in the early 1800s. It was an attempt to reduce math to a series of symbols and a series of rules that govern those symbols. And it's been shown by Gödel that it is impossible to do this with the integers. So Peano's axioms don't actually describe all of the integers. Like they don't describe all the things that integers can do. There are things that are true about Peano's numbers that cannot be proven in first order logic or second order logic.
Oh, okay. Okay. So what's first order logic and second order logic?
First order logic is like if, then, that kind of thing. Second order logic is like given a collection of things. So for example, first order logic might be like for all sandwiches, the middle of the sandwich is not the bread of the sandwich, or something dumb like that.
How about if it rains, then you're wet? If it rains and you're outside, then you're wet.
Okay, that works. But second order logic is like saying, given all the rainy days that can exist, there are perfect umbrellas for each one of those rainy things. So it's like talking about a whole set instead of just the individual variables. It's like like running instead of standing.
Okay, I think I get it then. So
and it'll become more obvious as stuff goes on.
Okay, so basically like set notation, like we're talking about a group of things, but the individuals within the group, is that kind of?
Yeah, like well, for example, the axiom of induction, which we'll get into, is second order logic.
Okay. Are you going to put this up on the website? To like have like, you should have like a step-by-step thing on the website to just show this particular proof just alone.
Yeah, actually, if you go to breakingmathpodcast.com/papers.html, you can find all this there. So we're going to start with the axioms. And the first one is very simple, and you're going to be like, what? Is 0 is a natural number.
Okay.
That's the only one that we actually define is 0.
Simply because we need to say that nothing exists and we need a symbol for that?
Well, we have to start somewhere. Because the natural numbers, we should probably talk about those. The natural numbers are 0, 1, 2, all the way to infinity.
I thought natural numbers were 1 to infinity and whole numbers that contain 0.
That is a really old definition. I think it's like 70, 80 years old.
Really?
Like, I mean...
I just taught it last week.
No, yeah. I mean, natural numbers, it really doesn't matter if it starts at 0 or 1. The original natural numbers, they started at 1. Now they are usually taught starting at 0.
Okay.
So it honestly doesn't matter.
Either way, we just needed to define 0.
Mm-hmm.
Okay.
And it's useful to define addition, as we'll see in a second. So for all natural, this is the axiom number 2, and we're going to go through all 10.
Okay.
For all natural numbers, x equals x.
Wait, before we go through this, might be helpful. I'm just curious. Did we already say this? We're going to go through all 10 rules, all 10 axioms.
Yeah.
An axiom is like a rule, yes?
An axiom is a foundational concept.
Okay.
So, for example, these are just things that you can't argue, that are taken as literal truth, and then you build the system from these axioms.
Peano wanted to do this because he was trying to explain how to work with integers.
Well, not necessarily just how to work with integers, but so in a formal system such as this, a proof is derived from the axioms. The axioms the axioms are manipulated together, and you derive what's called a sentence from the axioms. And a sentence is the same thing as a proof. So if you arrive at something, then you have proven it.
Okay.
Now, there's 2 properties that a system can have. In an axiomatic system, something can be complete or it can be consistent, but it can't be both if it's sufficiently complex. So if it's complete, that means that it describes all the properties. Consistent means that you can't prove that false equals true.
Okay.
Because if you could prove false equals true, you could derive any proof. So if for example, the Peano's axioms could be combined in some way which they wouldn't be consistent, which is false. They've been proven to be consistent with logic outside of the axioms by necessity. That means that there are certain theorems that cannot be proven from the axioms.
Okay, but they just need the axioms in order to build this system of explanation or proof.
Yeah, I mean, one thing I want to get across too is that formalism is no longer a very big goal for math. At the time, it was thought that math could be described using just axioms completely. And basically, Gödel's incompleteness theorem, which we talked about, is that basically the system can either be complete or it can be consistent, but it can't be both. And of course, an inconsistent system is more useless than an incomplete system.
Okay.
Because then it doesn't prove anything.
Okay.
And also, so now we're going to parse the, what I said was obviously for all natural numbers x equals x. So we're going to be talking like this for a while. So we want to discuss what it means. For all something, there is a condition, means like, you could say something like for all fish x has gills.
Okay. Basically, it's just describing it.
And the opposite of for all is, does not exist.
So for all fish, wings do not exist.
So let's say our statement is for all fish.
That's probably, mine was not probably a good example.
Well, I mean, for all fish x has wings. The opposite of that is there exists a fish such as the fish does not have wings. This is first order logic.
Okay.
And also, and second of all, we said for all natural numbers x equals x. But we can make that even simpler by saying for all x is a natural number implies that x equals x.
Okay. Actually, I like that better.
Yeah, but it's a lot longer. So you just say for all natural numbers x, so for all people x has a head. For all fish, that's a true statement, right?
Yes.
For all fish have lungs is an untrue statement.
Agreed.
But there exists a fish
with lungs.
Such that a fish has lungs is true.
Yes.
And those two are not opposite statements because the opposite of a true statement can't be false. So the opposite of the other one would be of the incorrect statement. No, for all fish have lungs.
I feel like it's sort of the rectangle square thing.
Or I mean, no, it would be that there does not exist a fish that has lungs. But sorry, continue.
Okay, for me, it feels like we're talking about the rectangle square thing. Like all squares are rectangles, but I mean, all rectangles are not squares kind of thing.
It's related to that. So, I mean, just to get the subtle distinction, there's a true statement, there's a false statement for all fish have lungs. There's the opposite of that statement, which is there exists a fish such as the fish does not have lungs. Then there's the...
But that one's true too.
That one's true. The first one is false. All fish have lungs.
Right.
Yeah, that's false. The opposite of that is some fish don't have lungs, which is
true.
Which can be written as there exists a fish X such that X has lungs.
Yes.
And then you have the completely different statements. There exists a fish with lungs.
Okay.
And which is true. And the opposite of that is all fish don't have lungs, which is false. So you can see the subtle distinction between those four.
Okay.
All right, so x equals x. That seems pretty obvious, but we have to define it. Otherwise, we don't know what equals what.
Okay.
All right, next one, number 3. For all natural numbers x and y, x equals y means y equals x.
Okay.
So like so if 2 plus 3 equals 3 plus 2 means 3 plus 2 equals 2 plus 3. It's reflexive, basically.
Exactly. It makes sense.
Yeah, and then we have basically the transitive property of equality. So for x, y, and z, x equals y and y equals z means x equals z.
Of course.
Yeah, so if I'm the same age as Taft and Taft is the same age as Leonidas, then I'm the same age as Leonidas.
Sure.
For all natural numbers x, this is the next one. If y equals x, then y is a natural number.
Because x is a natural number, so therefore y is a natural number. Yeah.
Yeah, everything that's equal to a natural number is a natural number.
Okay.
Then the next one defines what's called the successor function. For all natural numbers x, the successor of x is a natural number. So the successor function is just plus 1.
Exactly.
So the successor of 23 is?
24.
Successor of 0 is?
1. And we're not dealing with negative numbers, right? So we're just in the natural numbers, correct?
Yeah, exactly.
Okay. Either way it's plus 1, but still.
So the next one says that if we have two natural numbers, they are equal if and only if the successors are equal.
Okay, that makes sense to me.
Yeah, so like if we know that two numbers are followed by the same number, they're the same number.
Yeah, I mean, but basically you're just like 5 is equal to 5, then 6 is equal to 6.
Yeah, exactly. And vice versa.
Sure.
For all natural numbers x, the successor of x is not 0.
That would make sense, because even if x were 0, then the successor would be 1.
Yeah, because like the successor of -1 could be said to be 0, but -1 is not a natural number.
Exactly.
And the last one is, and all these so far have all been first order logic. This last one is going to be second order logic. And it says, for a given set k, if 0 is in k, and for all natural numbers x, if x is in k, implies that successor of x is in k, then all natural numbers are in k. So let me break that down a little bit. So we have a let me explain how induction is used first, and then explain how this describes it. So if we want to prove that all dominoes fall over if you topple the first domino, how would we prove that using induction?
You would say if the second one falls over when the first one hits it, then...
Well, we start only with the first one.
Well, if we tip, but it has to have an action after it, yes?
Oh, yeah. Well, but we'll see. That's the second part. So.
So if we tip the first domino over and it knocks the second one over?
Almost. It would be even more elementary than that.
Okay, go ahead.
So the statement is all dominoes fall over if we tip the first one over, right?
Oh, so we need to say if we tip the first one over.
So does the first domino fall over? Yes or no?
Yeah, because we tipped it.
Exactly.
Oh, if we tip the first one over, then it falls?
Yeah.
Okay, got it.
Now let's say that the nth domino falls over.
Okay.
The action that has is to knock down the n plus first domino.
Yes.
Therefore, all dominoes fall.
Okay.
So basically it's saying that if you could show that the first one is true, and that for any one that you pick, that the next one will be true based on that one being true, then all of them are true.
Okay.
And dominoes really helped me figure that out.
You never really considered the case where the dominoes weren't close enough, and so the domino fell and it hit the ground, and then it didn't knock it over.
Well, a property of one of the axioms in our domino little universe is that dominoes knock over dominoes invariably.
Oh, okay. And that they're equidistant from each other, so that you set them the right distance apart. They're definitely not going to have that space to fall.
Well, that would be implementing the axiom in something else, embedding it.
Oh, okay.
So that would ensure that the axioms are followed, but it's a correlation. It's a homeomorphism.
Basically, in other words, you're just saying if you tip over the domino, it will fall, and therefore...
If you tip over the first one, it'll fall because it's tipped over. If the nth one is tipped over, then the next one will fall over. Therefore, all of them fall.
Got it. Okay.
And so let's look at the definition again. For a given set k, if 0 is in k, and for all natural numbers x, if x is in k implies that the successor of x is in k, then all natural numbers are in k.
Yes.
So k here is the statement. So let's say if some number is in k, then it means that domino number n falls over. So 0 is in k because the 0th domino does fall over because of the tipping property. Mm-hmm. And if n is in k, that means that the nth domino fell over, right?
Yeah.
Which means that the n plus first domino fell over, which means that n plus 1 is in k. Therefore, all of natural numbers are in k, which translates to all dominoes fell over.
Interesting. I feel like it's pretty easy to understand without the domino analogy. Personally, maybe I'm thinking it's too easy. Like, in other words, basically you have a set k contains x has already been defined as a natural number, and we're saying that x plus 1 is also in this set, so therefore
Well, let's do a little bit more of a complex example, then maybe
Okay.
that'll drive it home.
Okay.
So the sum of 1 to n is n times n plus 1 all over 2, right?
Oh my gosh, that was a big old huge jump. But yes, I do know that. I gave that to you when you were 7. Do you remember that?
I do.
Okay.
But
I gave that to you to solve. Figure out this formula. Anyway, or create the formula. I think I gave it to you. Anyway.
it was done on many paper plates. But let's test out this formula with the first natural number, which is 0, right?
Yes.
So n times n plus 1 over 2 is 0 times 1 over 2, right?
Exactly.
Which is 0.
Of course.
Is 0 the sum of all natural numbers up to 0?
Yes.
Yeah, so it works for 0, right?
Yeah.
So now let's suppose that the sum up to n is equal to our formula, right?
Okay.
So this is the sum of all numbers up to n, right?
Okay.
So the next term, we would have to add n plus 1 to that.
Yes.
And if we do that, then the whole thing factors into n plus 1 times n plus 2 over 2.
Right.
Which is equal to n plus 1 times n plus 1 plus 1 over 2.
Right.
Which is our formula for n plus 1.
Right.
Therefore, therefore it describes the next number. And therefore, we have proven that that by induction that this formula is valid.
Okay. Okay.
And here k is a set of natural numbers. K is a set of numbers such that 1 plus ... to n is equal to our formula. So that is how we define k.
Okay.
But we're not going to define k in all of these. We're just going to use the intuitive way of doing it. I just wanted to drive home that it is possible using second order logic to define induction. So now let's define addition real quick, because we're going to prove that n plus n equals n plus m, right?
Yes.
So we have to define addition. So, and these are the last two definitions that we have. So for all natural numbers n plus 0 equals n.
Uh-huh.
That seems pretty self-explanatory.
Sure, that's identity.
And for all natural numbers m and n, m plus a successor of n is equal to the successor of quantity m plus n.
Okay.
So like 2 plus 3 is equal to 2 plus 2 plus 1 is what it's saying.
Okay.
So, and that's useful for addition because let's say we're doing 2 plus 2, right?
Wait, can you say that again?
So let me do it with 2 plus 2.
Wait, do the n plus n thing again.
M plus a successor of n.
Which is going to be n plus 1.
No, M plus a successor of n.
Yeah, isn't the successor of n plus 1?
Oh, you said the whole thing was n plus 1.
Oh, no, I meant like m plus n plus 1.
Is a successor of m plus n.
Oh, okay, yes, that makes sense.
Yeah, so it's useful for addition because let's say we're doing 2 plus 2, right?
Okay.
2 is a successor of 1, right?
Yes.
So 2 plus 2 is a successor of 2 plus 1. Now let's do 2 plus 1. 2 plus 1 is equals to is a successor of 2 plus 0.
Yes.
And then so the
Go
successor
forwards. Go forward.
Yeah, and then we're going forward now that we're down to this.
Oh, I see. Okay.
And then we have the successor of 2 plus 0 equals 2, right?
2 plus 0 equals 2, yes.
And the successor of 2 is
3.
And the successor of 3 is
4.
And so we have our answer.
Oh my God, that's so weird. We went backward to go forward?
Yeah, that's the cool thing about axioms and is that it's just manipulating symbols around. That's what makes it so attractive because if Gödel's incompleteness theorem didn't exist, we could just have a math machine, basically. That was what Hilbert was working on and hated Gödel for.
Math wars.
Oh yeah, math wars are totally a thing. We should do an episode on that.
You actually should. Or do like thievery or plagiarism or whatever. There's probably lots of that too.
So we know that n plus 0 equals n, right?
Yes.
How would we prove that 0 plus n equals n?
Probably with another axiom.
No, we no more axioms, no more definitions. We have everything we need. Induction. And the reason why is because the statement is 0 plus n equals n, right?
Yes, but we proved that 0 plus n equals n
We
just in the
proved that-
step before.
We proved that n plus 0 equals n. We showed that's a definition.
Okay, so we proved that n plus 0 equals n. And now you're saying why is 0 plus n equal to n?
Yeah.
Okay,
because-
so how are you going to induce that?
So 0 plus 0 equals 0, right? Mm-hmm. We know that because we switched the 0 that we're focusing on.
Yes. I got it. Okay, and then you're going to just change the order?
Yeah. And so, not necessarily change the order because anything plus 0 is that thing, right?
Yes.
So we are now just using the n as the 0 that we're adding to the 0 that's always there.
I get it, yes. So you just substituted 0 for n, right?
Yeah,
okay,
so it works
0
for
plus
0.
0 equals 0.
So now let's suppose that 0 plus n equals n.
Okay.
Now we know that if x equals y, if and only if successor of x equals successor of y, right?
Right.
So that means that if we have 0 plus n equals n,
okay,
then the successor of 0 plus n is equal to the successor of n.
Okay.
And remember that the successor of x plus y is equal to x plus the successor of y?
Say that one again.
Remember that x plus the successor of y is equal to the successor of x plus y and vice versa?
Yes.
So what would the successor of 0 plus n be?
The successor, that's a hard word to say. The successor of n.
0 plus the successor of n.
Yes.
Which is very important.
Sorry, I didn't put the 0 because I figured it was, you know what I mean? Like
yeah,
0,
you have to be very careful with these.
Yes. Okay, 0 plus the successor. I can't say that successor of n. There you go.
And so now we have the statement 0 plus the successor of n equals the successor of n.
Okay.
So we've proven the statement for the successor of n based on n.
Exactly.
And now we've proven that 0 plus n equals n by induction.
Exactly. Okay, gotcha.
We're going to prove that the successor of m plus n is equal to the successor of m plus n.
Okay.
So let's say m is equal to 10.
Okay.
And n is 5.
Yes.
We're saying that the successor of 10 plus 5 is equal to the successor of 15.
Which is the same thing, yes, because...
And remember before we would have been saying that 10 plus 6 is equal to the successor of 15.
Okay, so we're just reversed order. We just reverse ordered this thing.
Yeah.
Okay,
before it was m plus the successor of n
yes.
equals the successor of m plus n. But now it's the opposite.
Okay, I got it.
Or vice versa.
We just switched it around. So basically 11 plus 5 is equal to 16.
Yeah.
Okay.
So let's prove it for 0. And let's do induction on n. So the successor of m plus 0 is equal to what?
M plus 1.
Yeah, the successor of m.
Mm-hmm. I need to use the words, not the 1 plus
because
1.
remember, we're doing informal stuff. Sometimes when you're doing fractions, you use 2 divided signs because you really want to drive home the point that this isn't division. It is something that symbolizes division.
Okay. Think I got it. You know what I mean? It's all kind of a little bit new for me, but yeah.
Yeah. And of course it's equal to the successor of m because by the axiom n plus 0 equals n, right?
Sure.
So now we've proven it for n. So now let's prove it. And this one is kind of a involved one. So the successor of m plus n equals the successor of m plus n. We're going to suppose that. We're going to assume it's true for a second.
Sure. Wouldn't we already prove it?
No, we haven't proved it yet. We're proving it now.
Okay, I think I just misunderstood where the successor went. That's okay.
Well, successor of m plus n is equal to the successor of m plus n.
Got it. Okay.
So remember that if x equals y, then the successor of x equals the successor of y?
Yes.
So that means that we could set the sides equal to one another using the successor function.
Oh, okay. So we're going to work both sides of the equal sign, basically?
Mm-hmm.
Oh, okay.
So now we have the successor of m plus n is equal to the successor of m plus n.
Okay.
It's basically saying that 1 plus 11 plus 5 is equal to 1 plus 1 plus 15. If m is 10 and n is 5, for example.
I was going to say, okay. I just want to make sure. He said 11. Yeah, I got it now. If it's 10 and 5, that makes sense.
Yeah.
Okay.
So now let's look at the left-hand side. The successor of quantity, the successor of m plus n, end quantity. What we can do with that is because we know that the successor of x plus y is equal to x plus the successor of y, right?
Yeah.
So if we set x to a successor of m, right?
Okay, so now we're substituting in?
Yeah. Yeah. You always substitute in when you're doing axioms. This whole time you've been substituting.
Right.
So we know that. So if the successor of m plus n, we take that. We know that that's equal to the successor of m plus the successor of n, right?
Uh-huh.
Because, for example, just to give an example, if m is 10, then the successor of m is what?
Wait, and a real example, 11?
11. And then if n is 5, then 11 plus 5 is?
Well, 16.
And the successor of 16 is?
Is 17.
Yeah. And the next line down, we have the successor of m plus the successor of n. And they're the equal because if we set x to the successor of m and then y to n, we just move the successor function from the outside of everything to the inside. So we have that the successor of m plus the successor of n is equal to what the right-hand side was already, which is the successor of m plus n.
Okay. So basically you're just pulling off that x, the successor of x and successor of y initially.
Yeah, you
and
just
you're
move them
substituting
around.
in various things in order to get to that point.
Yeah, and now we work on the right-hand side. On the inside of the successor function, we have successor of m plus n, right?
Which we've proven is equal to the successor of m plus n.
Yeah, so now we have the statement, the successor of m plus the successor of n is equal to the successor of m plus n.
Yeah, this gets a little tedious with all this like successor stuff. And,
Oh, it really does. This kind of math is extremely tedious.
Yeah, and I would assume notation is incredibly important. It's visually though.
It's not only important, it's literally the whole thing. The whole thing, because these can be represented using numbers, for example.
Are you telling me?
You have a number equal to this function.
Okay, are you telling me that before they decided to write all this down, they used to talk? They used to speak math like this?
Well, in a way, yeah. Yes, absolutely. Like, for example,
Like with the words?
Yeah, this is the same era where where I can't remember which mathematician tried to formalize Euclid. Because Euclid, his elements, like a point is that which has neither length nor breadth. Like it's hard to make that into an axiom. I've tried. It's pretty fun.
Oh, yeah? Mm-hmm. So, well, that's geometry, though.
Oh, yeah. And this is that would be axioms for geometry.
Right.
And these are axioms for the integers. So in the same way that Euclid defined things
Right.
for his book, this defines things for a huge number of integer problems.
Which is funny. I feel like the easier the understanding, the harder the proof is to understand, if that makes sense.
Yeah, because it's so intuitive that you don't really know how to make a statement that's falsifiable.
Yeah.
Because it just seems so obvious that the opposite seems to be only the lack of that thing.
Exactly. Like to say 1 + 1 is 2 doesn't even seem like there's ever an argument or even a discussion necessary.
Yeah, but this allows us to talk about the integers in a very interesting way. There's also axioms for set theory, and some of them compete with each other. For example, there's the axiom of choice, which says that given an infinite number of sets, you can take one item from each set with a certain property. But if you take the axiom of choice, you can prove that by just cutting up a sphere into different points and moving the parts that you cut up around and then recombining them, you can make two spheres. You never stretch the pieces. You never change the size.
That is bizarre.
Yeah, right?
Oh, goodness. Okay. So
the Banach-Tarski paradox.
I assume that obviously they do this for a reason. It's just kind of funny if it's not particularly your discipline of study, it just seems funny. You know what I mean? But
Mm-hmm.
I get that it has to be done for a purpose.
Well, it was done for a purpose for a while. Again, like most of math now isn't trying to create some overarching all of math kind of thing. It's just people solving problems.
Probably because people already did that stuff.
Well, they tried to, and Gödel proved that it's impossible.
Oh, okay.
Like this is like the Principia Mathematica or Principia Mathematica. I don't know how to pronounce it. By Whitehead and Russell. I think on page 200 they prove that 2 + 2 = 4 or 1 + 1 = 2.
Yeah.
But and it just builds up to that. And that was an attempt to codify all mathematics. And people thought that it actually did, but then Gödel was like, nope.
Oh, okay.
And everybody kind of tore their hats in frustration.
Tore their hats.
Yeah, as you do.
When they were wearing hats.
Yeah.
What year was this?
This would have been 1911.
Okay, they'd be wearing hats, but not inside.
So anyway, now we're going to finally prove what we set out to prove. That m plus n equals n plus m.
Finally.
Yeah, right? So m plus 0 equals what?
M?
Yeah, by the rule n plus 0 equals n.
Sure.
And then we proved, remember the first proof we did was 0 plus n equals n?
Yes.
So 0 plus m equals m. And therefore m plus 0 equals 0 plus m by basically the properties of equality that we define.
I was like, is it transitive property-ish?
Yeah, because we proved that m plus 0 equals m and 0 plus m equals m. So if x equals y and y equals z, then x equals z. That's the property we're using.
Transitive property. Yeah, okay, gotcha.
So now suppose that m plus n equals n plus m. That means that the successors are equal, right? Since the thing would be equal.
Yes, of course.
So the successor of m plus n equals the successor of n plus m, right?
Right.
Now we can break this down on both sides. So the left-hand side, we could change that to m plus the successor of n, because we proved that the successor of m, but because there's a rule that the successor of m plus n is equal to m plus the successor of n.
Wow, that's really getting tedious to say, isn't it?
Right? But we only have one more step and we're done.
Okay.
Finally, we have m plus the successor of n equals the successor of n plus m. So now we're going to look at the right-hand side, the successor of n plus m. We can make the successor function go in the n by the lemma that we proved. Remember we proved successor of m plus n equals successor of m plus n?
Yes.
So that means that s of n plus m is equal to the successor of n plus m.
Yes.
And so now, since we've proven both sides, since we've done both sides, we have the statement m plus the successor of n is equal to the successor of n plus m.
Right.
And therefore, we have our thing proven by induction.
Exactly. Wow. That was a long induction.
Yeah, I mean, this was like, I had this proof in my Math 401 class, and I remember doing it over and over and over again.
Is this
just because, like, to get it down right? Because there's like different ways to do some of these parts.
Interesting. So they still teach it?
Oh, yeah. I mean, Terrence Tao has a very good book on analysis. I can't remember the title right now, but he discusses this in there.
Interesting. So it's not ancient. It's not like as if nobody talks about it. It's just.
Oh yeah, it's just that we're not trying to actively create rules that describe everything anymore.
Okay.
We're just using rules and understanding them for what they are as human tools.
Okay, got it.
So that was the first problem episode of Breaking Math, and of course we had on Diane Baca. Anything you want to prove? Anything you want to plug?
No, I don't, but I do think it's really helpful to see it.
Oh yeah, and if you'd like to see it, you can go to breakingmathpodcast.com/papers.html and it'll be up there.
Awesome.
Signing off.